What is variability? In general terms, it refers to how spread out a group of scores is. You will often hear the term variability, spread, and dispersion used interchangeably. They all refer to how spread out a distribution is. For example, let's look at the two distributions of classroom test scores shown here. Although they both have means of 7, it's obvious that the distributions are quite different. Specifically, the scores on the left graph are less spread out than the scores on the right graph. Said a different way, the differences among students are much less on the left graph than on the right graph. Just as there are several measures of the center of a distribution, there are many measures of the variability of a distribution. 4 are used frequently: the range, the interquartile range, the variance, and the standard deviation. We'll now look at each of these 4 measures of variability in more detail. The range is the simplest measure of variability. It's the highest score minus the lowest score. Consider the 10 numbers shown here. The range is just the highest number, 99, minus the lowest number, 23, which means the range is 76. Going back to our earlier example of test scores, on the left distribution, the lowest score is 5 and the highest score is 9. Therefore, the range is 4. However, the variability on the right distribution is larger. The lowest score is 4 and the highest score is 10. This makes the range 6. A second measure of variability is the interquartile range, which is the range that contains the middle 50% of the scores. The interquartile range is calculated by subtracting the 25th percentile from the 75th percentile. If you'll recall our discussion on box plots, the 75th percentile is called the upper hinge or the third quartile, and the 25th percentile was called the lower hinge or the first quartile. Using this terminology, the interquartile range is referred to as the H-spread. Let's go back to our 2 different distributions of test scores. For the left distribution, the 75th percentile is 8, and the 25th is 6, making the interquartile range 2. For the right distribution, which has a greater spread, the 75th percentile is 9, the 25th percentile is 5, making the interquartile range 4. A related measure of variability is called the semi-interquartile range. This semi-interquartile range is defined simply as the interquartile range divided by 2. If a distribution is symmetric, the median plus or minus the semi-interquartile range contains half the scores in the distribution. Variability can also be defined in terms of how close the scores in the distribution are to the middle of the distribution. Using the mean as the measure of the middle of the distribution, the variance is defined as the average squared difference of the scores from the mean. The data from the left distribution in our earlier test score examples are shown here. You'll remember that the mean score is 7.0, and therefore the column deviation from mean contains the score minus 7. The column squared deviation is simply that column squared. One thing that's important to notice is that the mean deviation from the mean is 0. This will always be the case. The mean of the squared deviation is 1.5. Therefore, the variance is 1.5. The formula for the variance of a population is the mean of the differences from the mean. The Greek letter capital sigma means to sum. The Greek letter mu is the population mean. If the variance in a sample is used to estimate the variance in a population, then the previous formula underestimates the variance and the formula is modified slightly as shown in the bottom portion of the display. In this formula, S squared is the estimate of the variance and M is the sample mean. Note that M is the mean of a sample taken from a population that has a mean of mu. An important difference between the formulas is that you divide by n in the top formula and by n minus 1 in the bottom formula. Since in practice the variance is usually computed in a sample, the bottom formula is most often used. Let's take a concrete example. Assume the scores 1, 2, 4, and 5 were sampled from a larger population. To estimate the variance in the population, you would compute S squared as follows. First, you calculate the mean, which turns out to be 3. You then subtract the mean from each score and square the differences. Then, you add up all of these squares, and finally you divide the score by the number of numbers minus 1. In this example, this leaves us with an estimated population variance of 3.333. The final measure of variability that we'll discuss is the standard deviation, which is simply the square root of the variance. As you may have guessed from the symbols for variance, the symbol for the population standard deviation is the small Greek letter sigma, and the symbol for an estimate computed in a sample is S. Going back to our earlier test score distribution, if you take the square root of the variance of 1.5, you get a standard deviation of 1.225. The standard deviation is especially informative when the distribution is normal. This is because the proportion of the distribution within a given number of standard deviations from the mean can be calculated or looked up in a table. For example, 68% of a normal distribution is within 1 standard deviation of the mean, and 95% of the distribution is within 2 standard deviations of the mean. A detailed look at the usefulness of the standard deviation in normal distributions will be presented later.